All right, good afternoon, everyone. Thank you for joining me today to learn a little bit more about EMV, Android NFC APIs. We're going to just dive right into it. My name is Richard Kolkovich. I am a husband, father of 3, and a competitive athlete. I've been building software for about 2 decades now. That's right, I started building software when generics were new to Java. If you've never experienced that, well, those were dark days indeed. Been building with Moov for about 2.5 years. It is my first foray into fintech, and I have been loving every minute of it. It's been a great experience. I still feel like I know absolutely nothing, even though I've been there 2.5 years. So let's dive into some of the stuff that I do know. Here's our kind of roadmap for the day. We're going to start with a very brief history of credit card security. That kind of brings us up to the why of EMV. Then we're going to get into the what of EMV and a little bit of Android NFC APIs, then a demo of some card scanning on the Android phone. So I also was asked by my daughter on Monday before I left if I was going to be performing the chicken dance on stage. I assured her I would not because I want to be invited back to speak again. All right, the early years of credit cards. We have the first charge card in 1950, Diners Club card. 58 is when Visa joined the party with a general purpose credit card, and then MasterCard comes in 1966. All of these cards have embossed lettering with your cardholder name, your PAN, and your expiration date on it, and are processed through the zip-zap machine, aka the knuckle buster, aka the card imprinter. So security features of this were really pretty much non-existent. You had a signature on the back, and the merchant is supposed to match up the signature on the receipt with the signature on the back. Fraud vectors are many. Good old-fashioned pickpocketing. I could grab your wallet, take your card, and use it pretty much anywhere because there's no verification. Verification was manual. You had paper lists called bad lists that the networks updated every week, if you're lucky, month. So that card could be out being used fraudulently for a long time before it gets caught. You also had counterfeit cards. You could just make a PAN up and laminate some cardboard and make a card that goes through the imprinter just fine. If you have a merchant who is unscrupulous, you buy $10 worth of salami from your definitely not a mob butcher shop, they edit that receipt before they send it, and all of a sudden you get hit for $100, and they're pocketing the difference. So not a whole lot of security features in here, and then add on to that mail order, which starts to become a bigger thing in the 1960s, and there's just absolutely no protection on the card not present front. Then magnets, how do they work? 1970s brings magstripe technology from IBM. This gives us one benefit over the previous era, which is that you can electronically auth. It's still easy to clone these cards. You can now skim the track data off of the magstripe pretty easily, but when the merchant is scanning that card, then it can go out to the card network, and you get a thumbs up, you get a thumbs down instantaneously. You don't have to consult this paper bad list anymore. It wasn't really until the 1990s that we introduced the CVV. That's where you start to get a little bit of protection on the card not present side of fraud. This 3 or 4 digit code is printed on the card. It is never included on in the embossed data. It's never included in the track data, nor on the EMV chip, as we'll come to see. So fraud is the roadblock. EMV is our hero, the solution to the fraud, right? 1984 was the first chip card pilot in France. 93, it took almost a decade for the first standard to be proposed for EMV, and then another 3 years for the first actual specification to come out of that consortium. It was version 3.11. As anyone my vintage or thereabouts can tell you, that was a very good version number. 2002 is when Europe began wide rollout of EMV, and then we joined in about a decade later because we do things on our own time in the US. It didn't quite take off as expected, either in Europe or the US, so the brands had to introduce liability shift. This was their stick, or carrot, probably a stick, to encourage merchants to accept the cost and the trouble to upgrade their terminals by stating that at this date in the future, if you are not able to accept EMV, then you will be liable for certain types of fraud that come through you as a merchant. So that lit the fire under the collective butts of the merchants to just choke down that cost, get new terminals installed, and move on to our future. Card-not-present fraud has continued to climb throughout all of this, while card-present fraud has fallen, so EMV is doing its job. Notably, it's mostly happening on the single message side of things, whereas fraud is still increasing on the dual message side of things just due to the nature of the delayed capture. And also on the EMV rollouts, Europe, as many may know, went straight to chip and PIN. So you have a second factor of security, whereas the US adopted chip and signature, and then in 2018 we dropped the signature requirement. So it's not the best implementation of all of the security features of EMV. With that history behind us, we can get into the what the heck is EMV. What does EMV even mean? Can anyone hazard a guess? Anyone know besides Christopher Coyce? Nope. Points to the man from the card brands, Europay, MasterCard, and Visa. It was unimaginatively named after the three companies who collaborated on that initial specification. That's great. That tells us what it means, but that doesn't tell us what it is. Now, today, EMV Co. is the organization that maintains all of the specs around secure payment transactions. So this is the new version of that initial partnership. They talk about everything from how this card is shaped to the pinout of the EMV chip to the antenna, yes, the antenna that runs through this card, to the software that's running on the card, which is what concerns us. The antenna is how it's powered in the contactless world. When you dip, two of these pins provide power to the chip, and then an operating system runs on this little chip. It's really quite fascinating, and if you were at the Tap to Auth workshop yesterday morning, you got to see that in action, actually programming one of these chips to run an EMV kernel. So, concerning ourselves with the software side of things, how does an EMV transaction even work? Communication between the card reader and the card is over what we call APDUs, Application Protocol Data Units. There are a lot of acronyms, a lot of abbreviations coming up, so you guys should be ready for this. It is fintech after all. The basic structure of this is it's a serial command format. So it's a command followed by command data. Nothing special, no compression or weird encoding or anything like that. And this is the payments industry, so if you look at this closely, it kind of resembles SFTP. First step is to select the directory, the Proximity Payment System Environment, or PPSE. This is the reader telling the card, this is the application suite that I want to run. And the card will then respond. If it's a payments card, it will respond with a list of application IDs that it supports. If it's not a payments card, because this is an ISO standard spec for any sort of smart card communication, you just get a, sorry, I don't do that. So you can't use your hotel room key to take a payment or give a payment. You also can't use your credit card to open your hotel room. Once you get back that list, we have to parse it, of course. These are AIDs, which anyone who's done card processing is familiar with. These say whether it's Visa credit or MasterCard debit, Maestro, diners, all of the different programs and combinations thereof are enumerated in this AID list. So once you have that from the card, then the terminal has to select the AID it wants to run. So say, hey, I want to use Visa credit, or I want to use Amex credit. This has a ramification later on in the EMV kernel because each brand has a different kernel specification. So it's slightly, how you communicate with the card is slightly different between them. Once you select your AID, you get back the processing options data object list, the PDOL. This is basically a template. This allows the card to tell you, hey, terminal, this is the stuff I need you to give me so that we can proceed and create a transaction. So what do you do with that? You fill it out. You fill out the terminal, you fill out the PDOL and pass it to the get processing options command back to the card. This GPO command will then return you an application file locator, AFL. It is basically a directory listing of all sorts of other data that you can find on that card, be it the PAN and expiration date or certificate data, anything that the card, that you may need to read from the card to proceed with the transaction. And you don't know what data is where until you actually read those records off of the card. Finally, with all of that in hand, along with things like the transaction amount that you would have had input from the merchant, you can generate an application cryptogram. Now, as the name suggests, this cryptogram is encrypted. The keys to this exist in the card on the EMV chip and at the issuer, so that the issuer, when it gets this authorization request, can verify A, this data has not been tampered with, and B, I know no one has seen it. No one can steal any data out of it because it's encrypted. So you take the cryptogram, ship it off to your acquirer, it gets put into an ISO 8583 message, sent onto the network, and again, thumbs up, thumbs down, there is your transaction. In the words of the great Bill and Ted, whoa. That 6 steps is doing a lot of heavy lifting, right? And those 6 steps are all happening within milliseconds. So, good news for today, we only need to worry about steps 1 through 5. We're not going to get into the cryptogram, just steps 1 to 5 for today. Let's pause on that EMV, stick that in the back of your brain, and let's jump right over to the Android side of things. So, quick show of hands, who here daily drives an Android phone? Okay, that's a pretty good percentage. Of you Android people, who has never daily driven an iPhone? Okay, a couple of us, straight from the Palm Pre. And then all the rest of you iPhone users, who has never daily driven an Android phone? Okay, you guys have homework assignment for FinTech DevCon 2026, and that's to daily drive an Android phone. One more show of hands, who has been inside of an Apple store? Okay, the Apple developer experience is very similar to the Apple Store experience, right? It's beautiful, you've got your well-curated selection of items. There's every detail meticulously poured over, some subtle hip music playing in the background as you browse through the iPads and iPhones and UIKit and HomeKit and PassKit. PassKit contains a certified level 2 EMV kernel, allowing you to pick up that package and run with it, accept payments in your app. But if you see something, or if there's something that you want that you don't see, you're out of luck. Try snooping around and there's a bouncer that will redirect you kindly to the curated selection on the floor. The Android side is more like an abandoned Amazon warehouse. It's not pretty, but you can find pretty much anything you need if you dig enough. There are a couple of different ways to build a UI. If you need raw access to your NFC reader because you don't have a certified EMV L2 kernel, then sure, you can definitely find that. It's in a box over on the end of aisle 42. And mind the dead rats. Now, EMV has gone from the hero of the fraud story to the enemy. It is the roadblock for implementation of payment on an Android phone. We don't have an EMV L2 kernel. We have to do it ourselves. So the first thing we need is access to the NFC reader. In the Android world, this is declarative. So you start by stating that your app uses the NFC permission. Straightforward. This prompts the user to give you NFC permission when you install said app. And then you also have to state that you use the hardware feature of NFC. And in this case, we're saying that it is required. That will prevent the app from being installed on a phone, if there is such a phone in 2025, without NFC hardware. Most of the time when you're building an app with NFC, you use something we call an intent filter. This allows you to tap your phone onto an NFC tag or a device, and the phone will run through all the intent filters, the Android operating system, and basically ask, hey, do you want to handle this? Do you want to handle this? And it allows an application to then launch from the background. So if you tap your phone on the hotel room door, ideally, then the hotel room app could load your digital key and unlock your door for you. We don't need to worry about that because we're going to be explicitly saying, hey, I want to scan a card, and going from there. So we're going to use the ISO DEP interface for Android. This provides an ISO 14443-4 connection. Don't worry, there won't be a test. The ISO 14443 is the standard for contactless smart card communication. This governs, again, all things that operate across NFC and communicate in this way. The -4 part is for protocol specification. 1 through 3 are all for other aspects of the contactless communication. So this is kind of the building block. This lets us send and receive raw bytes to our card, to and from our card. Reaching back to the EMV section, the APDU, this is what that looks like. You've got a class of instruction, which is either ISO. Again, this is the same ISO that I was just talking about, or proprietary, which will be EMV-specific commands. You have an instruction code, and then 2 parameters, which are usually used for offsets because they're just 1 byte apiece. Then you have a length of data and then a command data, so you can provide arbitrary command data for that instruction. And finally, there is the byte that is always 0, the length of expected response. It's in there. You always set it to 0 because you should always be doing a bounds check before you allocate your arrays anyway. First step, selecting our PPSE. There are 2 payment systems. The PSE is missing the proximity part, right? That second P. So that is used for the DIP version of EMV processing, whereas the PPSE, the one we're concerning ourselves with here, is the NFC version. So here's a class to kind of represent all of that so we don't have to worry about random byte arrays. You can see this is just basically a Kotlin version of that diagram I showed a couple slides back. The select class is already modeled out there. It's an ISO command, instruction A4, and the offset is 0, 4, and 0, and then you just pass in the byte strings of whatever you are passing. In this case, it is just the string topay.sys.ddf01. So we construct our command and send it to the card via the ISO DEP interface. So far, so good, pretty simple. Can anyone tell me why the Android developer was sad? Because he always had to suspend the fun. All right, we're going to parse the AIDs that we got back from that last, or from our select PSE command. So AIDs should be familiar territory to a lot of you. These are basic payment structures. Who can tell me what this AID represents? Anybody? This is bog standard Visa credit. You'll see this printed on your receipts. Once you get in the payments industry, like at least I do, I've started to really inspect everything that happens. So yeah, you'll see the AID on your receipts. This represents Visa credit. We get our response back from the APDU, or from the select APDU, and it is all in TLV format. So that stands for tag, length, value. You have 1 to 2 bytes for your tag, 1 byte for the length, and then n bytes for the value. Your value can then be another TLV structure, so you can have this whole tree of TLV data. For the AID selection, what we're looking for is tag 4F, which is our AID, and tag 50, which is an application label. These are contained within the file control information template, FCI template, which is tag 61. So this uses the Burr TLV library. It's just an open source Java library. Again, it makes it easier to read through this, so you don't have to just parse byte arrays by hand. So we look for that tag 61. That's the first thing we pull out. And then we're going to go through and look for the AIDs that the card has provided us with. So that's tag 4F, and then tag 50 is just the labels. Not all cards provide application labels, but they will provide the AIDs. So there's a little conditional case to handle that. After we get the list of AIDs, we're just going to select the first one that we get and send that over to the card. The response to that is the PDAL. This is tag 9F38 in EMV. So this is, again, our template. This is what the card wants us to give it. Sometimes, some cards, you won't get a PDAL back. In that case, you can provide just an empty array to, or an empty command to the get processing options command, which is our next step, and move along on your merry way. But this is a technical conference, so we're going to dive a little more deeply into a PDAL that I have gotten back from a Visa card, which looks like this. Since this is a template, this is not TLV format, this is in just T and L. So you split that up, you get your tag, your length. So you can see that this card expects tag 9F66 to be 4 bytes, tag 9F02 to be 6 bytes, and so on and so forth throughout the rest of the PDAL. Now, I know some of you guys are screaming at me silently in your heads since the TLV slide a couple back that said your tag can be 1 to 2 bytes, but there's no length for the tag. How do I know if it's 1 byte or 2 bytes? That is the first byte. If the last 5 bits, that's 5 to 1 since it's big endian, are all 1s, then you have a multi-byte string. So that is hex 0x1f, which will give you 3 zeros, 5 ones. So that mask you'll see in the code for checking whether or not you have a multi-byte string. So now we have to fill out that template, right? We have to give it the data that is required in the get processing options command. So this code, again, is very basic. It's by no means a full EMV level 2 kernel. It's just filling out the things that I have found in my testing, in my test cards. So starting from the top, we have our TTQ, tag 9F66. These are the terminal transaction qualifiers. This is just a set of bit masks that describe the capabilities of the terminal to the card. So this sequence here roughly states that it's a contactless terminal, it supports offline PIN entry, and it's a mobile phone. all of byte 4, half of byte 3, a couple bits in byte 2 are all reserved for future use, so there's plenty of room for the EMV spec to expand here. If you're interested in what all of these flags are, you can find those in EMV book A, table 5-4. They're all enumerated down there. So that is the first tag. The second and third are pretty straightforward. It's just your transaction amount and the secondary or cashback amount. And then finally, the terminal country code, that's the country code of the terminal, or that the terminal's operating in. So 840 for the US right here. And then we have tag 95, which is our TVR. This is kind of, whereas the TTQ is what the terminal is capable of, the TVR is terminal verification results. So that's like a point in time. This is the current status of the terminal. And what that allows the card to do is decide how to proceed with the transaction or if to proceed with the transaction, because this set of flags can indicate something that is off with the terminal. It could indicate that it's offline, or it can even indicate different variances of resistance in the NFC field. So it's pretty wide spanning in what it can tell you. Just sending a 0 here, or a set of zeros, just says that everything is A-OK. There's no anomalies detected on the terminal. The next flag, again, is the transaction country code. And then we have our transaction date, transaction type, which is 00 for a sale, 01 for a cash advance, 20 for a refund. That's all ISO 8583 spec. And then finally, a random number at the end of that. So we smash all that together into a byte array, and the GPO command is then TLV. So that's represented by tag 83. So you can see there that we are setting the tag 83, then our length, then our value, putting that into the GPO command and sending that back over to the card. Our response from GPO is the AFL, the application file locator. So this is, again, the directory listing of a bunch of other data on the card. Each of these is record locators, contains a short file identifier, and then record offsets. So the SFI is 5 bits out of the first byte, and then the next 2 bytes are the record offset. Because the read records command only reads a single record at a time, we have to expand all of the records out. So if you get offset 2 to 5, you have to read each of those individually. So that's what this code is doing, is getting your SFI by doing a bit shift to make sure you only get the 5 bits that you care about, and then expanding from the record offset, begin to end, read all those records, and then we can look for the data that we want, which in this case is track 2 data. So track 2 data is tag 57. You also have the PAN, which could be, which is tag 5A, and the expiration date, which is 5F24. Those go together. You'll get PAN and expiration date together or not at all, at least in my testing. You might get all 3 of these. You might get just track 2, you might get just PAN and expiration date. You might not get any of them. And they might actually not come from your record reading, but they might come in the command that we previously issued that gave us the AFL. So it's really more a set of guidelines than actual rules. If you thought it would be simple and consistent, then you haven't dealt too much with brand specifications. So this is where there is supposed to be a demo of putting all of this code to practice sitting on my Android phone. Unfortunately, my phone is not connecting to my laptop, so I can't actually show the demo because I had some problems getting the presentation going, so we're just going to skip over that part. I have it. I can show you. individually in close quarters after the talk is over. So we're going to end up ending a little bit sooner. But last slide here is kind of a what's next. If I had to prognosticate on security in general, specific to EMV security too, network tokenization is big on the card not present front. It's already here. That's how our watches and our phones have wallets. Those are network tokens. Your PAN doesn't exist on those devices. It's a token that's issued from the network that is linked to your PAN. The cool thing about the token is it's locked to the device. So you have to reissue that token if you switch devices. Where it's becoming more and more prevalent is online. So now you could, for instance, go to set up your bill pay for your Verizon bill. And instead of them storing your PAN and running that every month, they can store a network token. And when their database, not if, when their database gets exposed, then the PAN is not exposed. Furthermore, that token can be locked down not only to a device, but to an acquirer or even to the merchant, so that you can't take that token to a black market processor and commit fraud with that token. So that's pretty cool on the card not present front. In the EMV front, we missed the boat in the US on PIN, and PIN's not going to happen in the US, I don't think. But what we will see happening is CD-CVM. So this is consumer device cardholder verification method. This is built into the specification already, built into EMV already. The card can, usually it's tied to a transaction limit. So if you attempt a charge that is X amount or higher, then that ends up with a challenge. And this could pop up on your Capital One app on your phone and says, hey, is this you? Are you making this transaction? And using your fingerprint, your face print, your PIN, your blood sample in the future, you can verify that transaction. And now we're back to two factors. We have something you have, which is the card, and something either you are or something you know, in the case of a password or a PIN for that. So that I think is going to be the next kind of step for that card present security case. And because it's 2025, AI. Fraud detection is the logical place where that slots in. And if it's not already there, it's coming very soon. I can guarantee you that the card brands are working on whatever they can, however you can implement AI to make a smoother and more secure card experience. So with that, I'd like to thank you for your time today. I have been Richard Kolkovich. This QR code will take you to my website, which has a link to the actual code for the demo that I could not show today. But that code's available on GitHub. You can install it on your Android phone. Those of you who are about to go buy an Android phone and ditch your iPhone for good, install it on those phones. Play around with it. You can verify for yourself that it's not going to send me your PANs. It's not going to install a Bitcoin miner onto your phone either. Use the app, wow your friends and family, and just kind of maybe get the talk around security and credit cards going a little bit more. Does anyone, since I have some extra time here, anyone have any questions? I'll open up the floor right now. Cool, awesome. Well, if you think of anything or if you want to see the demo, I'll hang out in here for a little bit. I'll be out there for the rest of the day. Come find me, come say hi. Come try and convince me to try an iPhone. And just for my daughter, I'll do the chicken dance. Thank you very much. Enjoy the rest of fintech.